Yes, so hello, I'm Aleksey Veresov, software engineer at Hopsworks, and I'm going to talk about building Python-based AI systems with LLMs on behalf of Jim Dolan, our CEO. So there is a Beatles song which I quite like, and it has this line like, "I get by with a little help from my friends." And with the recent hype about LLMs, it seems that this line can be changed to, "I get high with a little help from LLMs." Yes, so for example, Google uses LLMs to write a lot of code. Their CEO recently declared that a quarter of their code is generated by AI. And this raises a question like how to control all of this, right? So they actually take a lot of actions to control these LLMs. Again, recently, like last month, an engineering director from Google wrote quite a lot about this on Hacker News and also linked this article on the ways they try to control LLMs. But let's ask a question like, how are LLMs used? Quite often in programming, they're used as a kind of productivity tools. So for example, Meta built 3 tools. One of them is like code search. The other one is code recommendation, which is essentially a system which provides you a sample from existing code base, solving the desired problem. And another one is like bug fixing. If you have used GitHub Copilot, that's more or less it. So LLMs, in this sense, are used kind of for meta-programming in certain sense. That is, they're used to kind of program programs, and commonly users ask them questions like, what is the best library to do something, or what are the possible ways to implement something, or what is the most efficient way to implement something. And in this sense, LLMs are kind of compilers from natural languages to programming languages, although that's quite questionable. They also can be seen as a kind of alternative IDEs in this sense, because IDEs are also tools which help developers transform their thoughts and into programs. But the question is like, which programming language should we use to be successful using LLM to meta-program it? And here, first of all, we have the problem of conciseness of programming languages. So Java is like notoriously wordy, while Python is like very, very concise and lightweight, simple, and so on. So maybe instead of like asking LLMs to generate highly complicated and long code in Java or C++ or Rust, it's better to ask them to generate programs in Python instead. It will be faster and probably with better results. The second thing is that weird symbols tend to confuse not only like humans, programmers, but also LLMs. So they seem to struggle quite a bit generating programs with like a lot of special symbols. It's hard for them to guess the meaning of all of them. And here Python is again kind of in a nice spot because, well, there are almost no weird symbols in Python. And the code is usually very well structured. Another point is interesting observation, first of all, is that SQL seems to be very hard for LLMs to generate. So there is this BERT benchmark, which measures how successful different LLMs or like frameworks are for generating SQL code. And the difference from the top performer and human performance is like around 20%, which is like a lot. And one of the reasons for this may be that SQL is based on rigorous math, and if you have tried to use LLMs and ask them some math questions, you can quickly observe that they hallucinate all the time, and they don't really check the details, and the result is almost always awful. So maybe that's the influence of rigorous math on SQL. And our point is that SQL code is usually highly entangled in the sense that you need to kind of also check all the details, all the names of tables, columns, whatever. Everything has to agree with the other parts of the code. So overall, this gives kind of an idea that maybe declarative programming, which is like highly intense, is less predictable than imperative programming for LLMs. So what about using Python as this kind of target language for LLMs? What about meta-programming Python with LLMs? Well, Python seems to be a very good choice because it's concise, it's very lightweight in syntax, doesn't have weird stuff in it. It's imperative, and most importantly maybe, it's very popular. So recently, like last month I think, GitHub declared that Python overtook the position of JavaScript as the most popular programming language. And this means quite a lot because LLMs are trained on open data from the internet. In part, they are trained using the source code from GitHub. So the more source code in a certain language you have, the better the results. So, okay, but what can you do as a developer of a framework or library to make your library more meta-programmable by LLMs? How can you make them more predictable for LLMs so that they can show better results for your users, which may want to use LLMs to write programs using your library or API? First of all, again, yeah, LLMs are trained on GitHub public source code, so put your good code in your repositories. Also, focus on API really well and like fix your API from the beginning, because the more diversity of API you have and the more different versions of the API you have published in GitHub, the harder it will be for the LLM to predict what to use in particular case. Yeah, also put your examples. That really helps LLMs to construct working programs. And yeah, make your API stable from the day one, as I said already. You can say that, okay, yeah, that's all good, but my repository, my library is like very small. LLMs are not touching this part of GitHub, I'm sure. So what should I do? The answer for this are two techniques, namely prompt templates and retrieval augmented generation. So as was shown in the previous talks, you can just embed the information about your particular library into LLM on the fly, kind of. Yeah, so in prompt templates, you can just directly put all of your docs and all of your available examples, and the LLMs will actually use this to construct some working programs. Another thing which you can do is you can integrate LLMs with external systems using function calling. In one of the previous talks, it was called tool calling. That's the same thing. So essentially, LLMs can ask the environment to execute something and get back the results and like process them or include them in their reasoning. So yeah, they can request the data on their own. And in case of generating programs, typing the programs seems to be quite useful, because then you can use MyPy or something like this as this function, which will check the LLM-generated code and hopefully dispel some of these hallucinations, kind of filter out the non-working programs, or at least larger portion of them. Yes, so that's kind of an architectural overview of this solution for like using LLMs with resource rags and function calling. Yeah. And one particularly successful example of this is Julius AI, which is a data analysis tool. It provides a very satisfying experience. Try it out if you can. So imagine we upload a CSV file and ask a CSV file with like salary data for different people marked with ethnicity and gender, and we ask this Julius AI to generate a plot grouped by these parameters. So what Julius AI will do, it will create a series of small Python programs which use pandas to transform the data, and then it will just plot the results using Plotly or Matplotlib. You can actually also ask it to use pretty much anything else you want. And if there is an error in one of these programs, then they just take this error and the code and feed it back to the LLM so that it can fix the error, and then they repeat this process, of course, with some limitation of iterations, but usually it works in one iteration. Yes, and very important here is that these programs which they generate, they kind of have no side effects. That is, they do not modify your database or something like this. They just extract some data, process it, and graph it. So it's very easy to do this testing just by running these programs. But once you have a program with side effects, then it becomes problematic, because this program during the testing can just mess all of your data and environments, whatever. Yes, so now let's talk about building AI systems with LLMs and Python in Hopsworks, kind of replicating this experience of Julius, maybe on a bit simpler scale. So one point here is that prompting can be seen as knowledge evocation. That is, you need to remember that LLMs kind of already possess all the possible knowledge. They are a very compressed way to store statistical information about pretty much everything. So kind of the challenge in using LLMs to do something is to provide them specific context so that they recall and apply this knowledge effectively. So in cases they don't do it just from the user queries, you have to use prompt templates and rags. And yeah, as I said before, prompting is knowledge evocation. So we just can use LLMs with a little bit of guidance from these prompt templates. For example, if LLM uses deprecated API of your library, you can just prompt it with direct number of the current version of your API, and it will actually recall the correct API and use it instead of the deprecated one. So that's an example of a prompt preamble, which is used to generate synthetic data using what is called logical model. That is a description of distributions, cardinality, and data types, and so on of your data. So here in the prompt preamble, our main goal is kind of to just provide the right context, kind of use the right words. Here they're like polars, data frames, faker, feature groups, Hopsworks. And then we just paste the whole of this logical model. So as I mentioned, it contains descriptions, cardinalities, maybe distributions as the last point. And this simple prompt preamble, which I showed previously, and just the logical model taken as it is, actually produces results in program, Python program, using Hopsworks API and so on, which works, and yeah, it's very easy to achieve this result. But you may ask, okay, looking at this previous logical model, right? It contains so much information. Is it really different from programming? Like, when it's such a detailed specification, what's the difference? But we believe that there is a difference because we didn't know how to use polars, how to use faker, how to create even columns with the expected data distribution and cardinality, how to build data frames in Hopsworks with pandas. And we even didn't know Hopsworks API to save the data frames. And still we achieved the result without knowing any of these details. So yeah, it seems to be different from normal programming. Now, let's talk about building AI systems with LLMs and FTI pipelines, which is feature training inference pipelines, which is one of the key features of Hopsworks. It's kind of the structuring idea behind it. And here the emphasis is going to be on the AI systems. That is, Julius and many of the other systems, they are tailored to kind of one-time use, while to be a system, you have to kind of be executed for a period of time and be evolving in some sense. So this poses some additional challenges. Yes, but first of all about these FTI pipelines. As I said, this is a structuring idea behind Hopsworks. And this allows us to guide LLMs to decompose the system into small modules instead of creating the whole system at once, which is much easier for them. And yeah, because of this pipelines framework, we have a very well-defined structure of models. We can run them separately to dispel the hallucinations, and then compose these models to the whole system. Again, standardized interfaces of FTI help here. As a kind of a point to remember here is that good software engineering is good for LLMs too, it seems. Yeah. So in short, let me introduce this feature training inference pipelines. Essentially, this is just a way to separate your data processing into your AI system into these three modules. And feature pipeline its goal is to take the data and put it into feature groups. That's pretty much it. Then you declare some feature views on these feature groups, which extract the information from these feature groups. Training pipeline uses this data from feature views to train the model, and then the model is saved in Hopsworks. Then inference pipeline uses the data and the model to make predictions, and also we save some logs to make evaluation of the model. Okay, now I will show one example of using LLMs to generate only the first part of this FTI architecture. Particularly, we are going to use LLMs to generate feature pipeline. Particularly, we are going to create feature groups from a CSV file. So the user just uploads a CSV file and maybe provides some additional instructions on what exactly he wants to extract from them, and the LLM kind of does the rest. So overall, the structure of our solution looks like this. So we're actually using LangChain also, as in the first talk. So we take the user query and the dataset from the user, pass it through three stages or steps, and report the results asynchronously via streaming responses, so that the user kind of gets low latency and can keep track of what's going on inside the LLM. Yes, so each of these stages looks more or less like this. We take the inputs, we place them into the slots in the prompt template. This creates the full prompt. We feed it to the LLM. LLM generates the summary of current step, like what it does right now. And it may produce some shell scripts, which I used to essentially do only one thing, pip install, in case import errors occurred. Or it generates a Python script, which in this case is executed. If it fails, the error message and the Python script itself are fed back to the LLM via prompt template. And if it succeeds, the context produced by it and the script itself are passed as the output to the next stage or to the user. So now the first part, this is kind of a shortened version of the prompt template from it. As you can see, we just put the user query and the dataset path here provide a lot of requirements. I listed some of them. We also have a system message saying, as always, kind of, you are an expert, la la la. And this is the result of this stage. That's like an actual result from performing this architecture. So we can see that LLM, as a first step, loads the data and transforms the column names to lowercase. Then it outputs some basic information about the shape of the data for the next step to use for data preparation. It counts some missing values percentages and the count of unique values, other stuff. And all of this data is passed to the next step via this analysis code point here, stage 1 code analysis. So that's the code from the previous stage, and the results are here in dataset analysis. And we pass the same user query. Now, in this second stage, the LLM goal is to provide the code which will transform the data according to the user query. So, yeah, system message, as always, is you're an expert, la la la. So in this stage, the generated code also loads the CSV, then it sets some settings, and then it actually prepares the data. Here it handles missing values, and here it provides the translation from integers into the format of labels which the user requested, i.e. Dead and alive. Yes, and now the final stage is just kind of assembling all of this and wrapping it with calls to Hopsworks API to actually save the created feature groups into Hopsworks. So that's an example of the feature group descriptions which it generated. So quite useful is that it also generates descriptions for each of the features, and this in turn can be used by other frameworks or workflows, other workflows, because this information can be used by other LLMs which will work with these feature groups afterwards. And this is the actual code which goes through the list of all of these feature group descriptions and saves them into Hopsworks. So that's a short recorded demo of the actual UI of this tool. So here we upload the data set, paste the user query, and we can see the streaming response. It's sped up. Yeah. Now we can see the summaries of each of the steps from the LLM, and we can see the final result, the Python script, which we can, in the next step, run and actually acquire these feature groups from the CSV file. Okay, so final part, challenges. I will rush through this. So in RAG challenges, we need to provide some metadata to the LLM. And as I pointed out earlier, Hopsworks provides a lot of it. So we have descriptions of pretty much everything, features, feature groups, feature views, literally everything. Another thing is that we have certain, it can be challenging to run the code because the generated code is not idempotent, so we cannot just run it to test it. We can use typing, or we can mock our stateful APIs so that it's possible to actually run the code without destroying all the data. We should run pip install libraries on import errors. There is also a problem of how to size and actually run the tasks. On Hopsworks, it's fortunately served by kserve and VLLM, so this question is handled much easier than it would be if we would do it manually. For agentic workflows, the question is how to guide users in creating these pipelines. And conversational text is very good. It's very flexible and easy to use in some sense. Plus, LLMs can be configured to be more or less pedantic. Alternatively, dialog wizards can be used for more rigid workflows. For evaluation, we really need to evaluate things because LLMs are quite chaotic. And yeah, that's it. So as conclusions, provide good docs and examples in your code. It's crucial to make LLMs work with your code. Dispel hallucinations with error feedback loops if you are building this LLM meta-programming system, so to say. Typing and idempotency help a lot here. Evaluate LLMs. And pay attention to security while running the LLM-generated code. Thank you.